Hello and welcome. In this video, I will explain how to solve a first-order autonomous difference equation using analytical method. First of all, we will take the homogeneous part of this difference equation, which is equal to yt plus 1 minus byt equals to 0. We will assume a trial solution in order to find the complementary solution for this equation. So for the complementary solution, we have a trial solution given by yt equals to a lambda raised to the power t. And lambda is an unknown root of the characteristic equation, which we will derive soon. So since yt equals to a lambda to the power t, if we iterate it for one period, we get yt plus 1 as a lambda to the power t plus 1. And therefore, we can write this equation as lambda times yt. Now, by naming these two equations as a and b and using them in equation 2, which is the homogeneous equation, we get our equation as lambda yt minus byt equals to 0. We can take yt common from this equation and it becomes y times lambda minus b equals to 0. Note that this equation says that the product of yt and lambda minus b equals to 0. So this would be true only if either yt is 0 or lambda minus b is equal to 0. However, yt cannot be 0. If it is the situation, then we would not have any dynamical system. Therefore, for this equation to be true, lambda minus b must be 0. And hence, we have lambda equals to b as the characteristic root of the characteristic equation, where the characteristic equation is lambda minus b equals to 0. Hence, the complementary solution becomes yt equals to a b raised to the power t. We call this equation t, and this is our complementary solution. In the second step, we will find the steady state value of the dynamical system. The steady state is the value where the dynamical system does not change its state. The variable stays the same given the time is changing. So we set yt plus 1 equals to yt equals to some static value y bar in our main equation 1. So equation 1 becomes y bar minus by bar equals to a. And by taking y bar common and getting rid of the coefficient, we get y bar equals to a upon 1 minus b as our steady state value. And this steady state requires that b should not have value equals to 1. Once we have the steady state value, we can find the general solution as the sum of complementary solution and the steady state. So we see that from equation above under complementary solution, we got yc equals to a b raised to the power t. And the steady state is a upon 1 minus b. In this general solution, the coefficient a is an unknown constant which we want to determine, and that requires some initial condition. Hence, we will find the particular solution. For particular solution, we assume that y0 is the initial value when time is equal to 0. So we set t equal to 0 in equation 4, which would yield y0 equals to a upon 1 minus b plus a b raised to the power 0, which means a. And hence we can find a as the deviation between the initial value and the equilibrium state. So once we know the initial value, we can also find the unknown coefficient a from the complementary solution of the equation and can substitute that into our general equation in order to yield the particular solution. So our particular solution takes the form where we have y equals to the steady state plus the deviation from the steady state times bt. To implement this method, let us consider an example where price in period t plus 1 is equal to 80 plus 0.9 times pt. So we will implement all the three steps. First of all, we find the complementary solution. Then we will find the steady state and take the sum of steady state and complementary solution to get the general solution. And if some initial value is given, or value of the series at some particular point in time is given, we can use that to find the unknown coefficient a in our particular solution. So let us do that. So step 1 would be find the complementary solution. For this, we will be assuming yt equals to a lambda raised to the power t in the homogeneous part of the equation. That means pt plus 1 minus 0.9 pt equals to 0. So this represents the homogeneous part. Then we have a trial solution. Pt equals to a lambda raised to the power t. And then we can iterate it for one period forward, so that pt plus 1 is a lambda raised to the power t plus 1, which means we can get the characteristic equation as lambda minus 0.9 equals to 0. Thus, the complementary solution is a times 0.9 raised to the power t. Now we find the steady state. In step 2, we will equate pt plus 1 with pt equals to some stationary value p bar in our main equation 1, and therefore it will give us the equilibrium value of p as 800. The third step is to combine the steady state solution and the complementary solution. So we take the sum of complementary and steady state solution to get the general solution as 800 plus a times 0.9 raised to the power t. Assuming the initial value is given as 100, then we can substitute that into equation 3 with t equals to 0, such that we will have value of a equals to minus 700. And therefore, our particular solution becomes 800 minus 700 times 0.9 raised to the power t. So this way we have solved the first order autonomous linear difference equation by applying analytical method. The next would be to analyze the stability of the system and the nature of the time path.